Yesterday we started talking about vectors, and we came up with several notation forms for vectors, and we came up with ways of moving around our little vector racetrack. Today we're going to take that vector arithmetic, of course I've chosen the wrong pen, and we're going to look at it a little bit more formally. All right, so you're heading, that one's not much better. Vector arithmetic. Alrighty guys, shh. Shh, 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 shh. Yesterday, or last lesson, I gave you the first type of vector arithmetic, and that was multiplication by a scalar quantity. Alright, when we multiplied by a scalar, what happened? So we had our vector, and we multiplied it by a scalar quantity, which is scalar quantities like 2, a half. What happened to our vector?
The magnitude changes.
Good. Our magnitude changed, but our direction did not change. And when we were looking at that, we can look at it graphically, but we can also look at it in component form. So for example, if I had 3i, that's my component in the x direction, and the perpendicular to that is our j, so 3i plus 2j, and we multiplied this whole thing by a scalar quantity. The scalar quantity in itself has no direction because it's scalar, so it is just changing the magnitude. So when we actually work this through, we use that distributive law that we have had since we started expanding brackets. If we were to do the magnitude of this, the magnitude of 3i plus 2j, how did we work out magnitude? Pythagoras' theorem. So we would then have, I'll cut that one out actually, we do the square root of 3 squared, that's in this direction, and because this direction is always perpendicular, we can just go straight into Pythagoras' theorem. So we end up with square root of 9 plus 4 is 13, and if we're going to then multiply that by the scalar quantity, we have a 6 here, a 6 here, and we end up with 6 root 13. Now if we are going for the magnitude of our multiple, then can someone pull out the calculator, because I'm not going to be able to do this in my head. 18 squared plus 12 squared is?
468.
468, which I'm hoping is 36 times 13. Which gives us back to our 6 root 13. So you can see that all we've done is change our magnitude when we're doing a multiplication by a scalar. Are there any questions about that particular bit of arithmetic? Okay. The next bit I want to talk about is vector addition. And you guys informally dealt with vector addition yesterday when you were playing your vector scalar game, vector racer game. What you were doing is every time that you made your first move, which most people did a first move of 2 straight up, you then added on to that one, and often you went sideways in some way, shape or form. Because we had our first vector plus our second vector, we can replace those with another vector that starts at the same point and ends at the same point as well. And this vector represents the vector A plus the vector B. Couple of things to note. Tails start with tails, and we end up heads to heads. Now, I want to show you graphically why this works, and then we will look at our 2 other forms. So graphically, if I started with my vector A, in the I component direction, I travel this distance. Agreed? In the perpendicular component, I travel this distance. Ooh. So, as I was talking to you yesterday, this is a bit like jaywalking across the road. I can break you up into going down to the crossing and then crossing the road directly, or you can wander across and risk getting hit by a bus. So we have these two components, and we can see that we could break them up to be anything we want. So M and N. So in this case, my A vector is actually M plus N. When I add my B vector, I'm going to do the same things. So in this direction, I have, I don't know, let's call it X. Oh no, what X is bad? P. And in this direction, I have Q. I've missed an arrow. And so again, I have that my vector B is the sum of vector P and vector Q. When I go for A plus B, I can just add my two vectors in this direction and my vectors in this direction. And I would end up with a vector that went from, running out of colours, A all the way to B, which would have this component in the I direction. I've got to go back and put my eyes on. And this component, or the sum of those components, in the J direction. Are we good? Can we see why that works? This is called the triangle law because we've made a triangle. And it has a lot of the same features as triangles and all the rules we've had with trig, which is one of the reasons we've done all of our trig stuff before we've arrived here. Later on, we're going to be using some of the angles, but for now, it's enough to realize that we're adding each of our components. The reason I wanted to take so long to do this is, let's look at a worked example. In component form, let's come up with vector A being I plus 2j, and vector B being, I don't know, minus 3I and 5j. When we are trying to work out my resultant vector, so A plus B, I can just add my component vectors. So I just need to look at, what's the number in front of the I here? 1 plus minus 3I. They're my I directions. They are my green ones. Heading up into our J direction, I have a 2 and a 5. So my component is minus 2, sorry, my resultant vector is minus 2I plus 7j. So I can add them this way and I can add them that way. Are we comfortable doing that? Does that seem logical? Yep. What happens when we change that to column form? What does my A vector look like now in column form? What does it look like? 1, 2. I direction, J direction. You with me? I'm adding minus 3, 5. Notice there's nothing obvious to say that these two are still like terms and these two are still like terms. That's exactly what we did here, but it was nice and obvious because they had all these beautiful eyes around them. Agreed? So when we do it in column form, we still do the same thing. 1 plus minus 3. 1 plus minus 3. It's still my I direction. My J direction is still 2 plus 5. My answer is still minus 2, 7. Are we good? So even though it looks like we might need to do something else, it's exactly the same idea.